Okay, so this is section 1.1, which I was planning on doing on Friday, but I'm putting the video up today, and the homework for it will be due on Monday. So the idea behind section 1.1 is that we are going to try to talk about the slope of a straight line, which is something you would have learned about in Math 21 or Algebra 1 class. And relate it to the idea of the slope of a curve, which is more of a calculus idea. So in applied problems for different situations like cost functions, we have the slope of the line. We think about it as a rate of change in that linear function. So for example, the cost function, we talked about having a variable cost and a fixed cost. And the variable cost in this cost function would be the cost for every unit that I decide to make. That means that every time I make another unit, the cost rises $3. So that is a rate of change in my cost function. Every new unit costs me $3 more. The $12 is a place that I start my cost function. So if I make no units, it still costs $12. But the rate of change in my cost function, the way the slope works is I rise $3 every time I run one more unit. And so we're going to be thinking in calculus that the slope of any kind of a function is going to be measuring its rate of change at that particular point in time. So if we use that intuitive approach to measure that slope is measuring a rate of change, we could do that same thing on a graph that's not a line, that's not linear. We could look at this curve here that's graphing a function, and we know it's graphing a function because it passes the vertical line test. But we could just take a little snapshot of this curve at this point B on the curve. We can see that the function looks like it's decreasing because as our x values get larger in a little neighborhood around B, the y values are getting smaller. So that's how we define a function being decreasing. And we could see that at a point A, the function is increasing because in a little neighborhood around it, as x gets bigger, as we go left to right, the function values also get larger. And it's also increasing at C, but we could make a comparison between how fast the function's increasing at A and how fast the function's increasing at C. And if we looked at that difference, we could see that it looks like it's increasing faster at A because the slope is steeper. So for every little change in x, there's a bigger change in y when we're at the point A than there is at the point C. So if we move a little bit to the right with our x value, the y value is going to increase faster at A. So we can use this steepness to compare rates of change on a curve. And that is what we're going to be studying very soon, and it's called the derivative. The derivative is a rule for the slope of a curve at any point on the curve. So we're going to have that idea that we're going to circle back to. But for now, we're just talking about a line, and we know that the equation of a line can be written in two different forms, either slope-intercept, where y equals mx plus b. M is the slope, and b is the y-intercept. It's actually the y value of the y-intercept. So we write it as a point. If my line crosses here, the y-intercept is technically 0, b, but we know that it crosses at a y value of b. And the point-slope form, where if you have a point, which is designated x sub 1, y sub 1, and these little ones are just ways to keep track of points. You could have x sub 2, y sub 2, x sub 3, y sub 3. The subscripts are just helping us distinguish which point we're talking about. Then the point slope form, you take y minus the y value of the point you have, and it should equal the slope of the line times x minus the x value that you have. And this just comes from the fact that we can come up with the slope between any 2 points by subtracting the y values and subtracting their x values and making a fraction. So this is just a rewrite of the slope formula. So the idea is that if you imagine walking along any line that you're drawing from left to right, if the slope is positive, you're going to be walking uphill. And we talked about that being an increasing idea. And if the slope is negative, you're going to be walking downhill. If the slope is 0, then the line's going to be horizontal and you'll be on a level surface. So positive slope would look like this. A negative slope would look like this. A 0 slope would look like this. And then the final type of slope that we can have is an undefined slope. And so if it's an undefined slope, the line is vertical, and the only way to go left to right would be to be like climbing a ladder going straight up. So an undefined slope looks like this. So positive, negative, 0, and undefined. Just a quick review of what you know already. All right, so an example of how we can use lines. If a manufacturer finds the total cost of producing X units of a commodity is 2X plus 1,000, the economic significance of the y-intercept and the slope of the line are this. The y-intercept, if cost is graphed on the y-axis and units are graphed on the x-axis, what the y-intercept of 1,000 means is that when we make no units, it costs us $1,000. So that means the y-intercept of 1,000 is measuring our fixed cost. And the slope, which is 2, is measuring our variable cost, just like we talked about earlier. Every unit that we decide to create, every time we create another unit, it's going to cost us another $2. So we'd move up $2 to make one more unit, and that's our slope. Now this isn't technically a line because we wouldn't go any further than an x value of 0. We wouldn't have negative number of units that we're making, so technically it would be a ray. But wherever this ray intersected, the y-axis is our fixed cost, and the slope of it is our variable cost. Example number 2, if we have an apartment complex with a storage tank that's holding heating oil, if the tank was filled on January 1st and no more deliveries of oil will be made until sometime in March, if T denotes the number of days after January 1st and Y denotes the number of gallons of oil in the tank, current records showing that Y and T are related by this equation would mean that when T is 0, there were 30,000 gallons in the tank. So the y-intercept of 30,000 would be the beginning amount in the tank. So at the very beginning of time, which we're counting as January 1st, there are 30,000 gallons in the tank. And the slope of negative 400 would mean that every day 400 gallons are used. And so we go down 400 gallons every day that we have after January 1st, and that would be a linear situation. It's not reality because some days we're going to use more oil than others, but if it is a line, it would mean every day. And these two words are what's indicating it's a constant decline in the number of gallons. Slope property number 2 is you can calculate the slope of any line if you know 2 points on the line. So if you know 2 points on the line, you're going to subtract the y values of those 2 points. You're going to subtract the x values of those 2 points in the same order. It doesn't matter if you decide to subtract them by starting with the first point, as long as you are consistent in the denominator. So you can choose whichever order to subtract. But the change in your y values, which is y2 minus y1, sometimes we call that the rise between your 2 points. And the change in your x values is sometimes called the run in your 2 points. And when you make a fraction, rise over run, you get the slope. So for this particular problem, the slope between these 2 points is one of your y values minus the other. So I chose this one, this y value first and this y value second. So then I'm going to have to use this x value first and the other x value second. I'm going to add because it's minus a negative. I'm going to add because it's minus a negative. And I'm going to get 5/2. So if you had chosen to go the other order, -4 minus -2 over -2 minus 3, you would have gotten -2 over -5, which is also, oops, what did I do wrong? Yeah, I did my x values on top, sorry, mistake there. Let's try that again. If you did it in the other order, but you kept y on top, which is the goal, you would have -2 minus 3 and -4 minus -2. You'd end up with -5 over -2, which is also 5/2. So it doesn't matter which order, you're going to end up with the same answer in the end. The idea of slope as that slope is a rate of change means that if I have any kind of a linear function, and remember we're moving from the notation y equals to the function notation. So in this case, we're using L because it's a line. So the function of the line in terms of x could be written as the slope times x plus b. And what it means is as x varies from one x value to the next, y is going to change from one y value to another y value. And using function notation, the y value for y1 is going to be the function evaluated at x1. And the y value for the second point is going to be the function evaluated at the second point's x value. So this again is just function notation for y1 and y2. And the way we calculate a rate of change then, if we go from x1 to x2, is we think about the change in y, which is the subtraction of these two y values, and the change in x, which is the subtraction of these two y values, and we make that a fraction. So y2 minus y1, x2 minus x1, it could be L of x2 minus L of x1. If we want to use our function notation, that could be the numerator. But that change in y over the change in x is what the slope is measuring, whether we're talking about a line or whether we're talking about a curve. If it's a line, the rate of change is a constant. But if we're talking about a curve, the rate of change is going to be different as you move through the interval. It's going to vary. It's going to be a different rate of change at x2 than it is at x1. So we're going to move from the idea of a constant rate of change means when I go from this point to this point, whatever I rise and run, that's how I get the next point. That's what makes a line. Rise over run stays constant, and that creates a line. But there are going to be times where the graph is going to curve. So my rise and run between these 2 points is going to be different than my rise and run for the next 2 points. The curve is going to have different rates of change depending on where you are. So our last example, if we have a cold front that's moving through a city and the temperature dropped 3 degrees Fahrenheit per hour between noon and 8, so it was a constant decline between noon and 8, and we want to express the temperature as a function of time and then find the temperature at noon, given that at 1 p.m. the temperature was 47 degrees. Or that means that if we plug the number 1 into the temperature function, we get 47 degrees. So we're trying to take all that information and write the function. And one piece of information we have right now is that when we plug 1 into the function, so we let 1 be our x value, the value that comes out is 47. So that's 1 point on this function that I have. The other information I have is the rate of change in the function. So it's changing 3 degrees per hour. It's dropping 3 degrees per hour, which means its slope is -3. So that means if I go to x equals 2, so my x has gone up by 1, my y value is going to go down by 3. And it's going to keep doing that until I get to 8 o'clock. So the only missing piece of this puzzle is what happens at time 0. So this was at 1 o'clock, but I'm allowing time to start at noon. So if I went back in time to when time was 0, x was 0, that means that going back, I'm going to have to do the opposite of what I did when I went forward. And that's going to have me start then at a 50-degree temperature at noon. And when I graph this thing, since they're telling me that that noon is the beginning of time, that's my value when x is 0. That is the y-intercept of this line. 50 is where 50 degrees is the temperature that matches with an x value of 0, which is called noon. And then it's decreasing from there at this constant rate. So my equation for the temperature is going to be -3x plus 50. And then I have to state that x equals 0 means noon. So that's an important piece of information. So when I plug 0 in, I get 50 out. When I plug 1 in for 1 o'clock, I get 47 out. And it's going to keep doing that until I get to 8 o'clock. So my domain for this function is I want to use values from 0, and then I got to figure out where am I going to end. So this was noon, 1, 2, 3, 4, 5, 6, 7, 8. I'm supposed to stop at 8 o'clock. That would be an x value of 8. So that's how I'm going to create my function, and this table can help me sort of check myself to make sure I've got the right x value matching with the right time. So I could create another little column here, noon, 1 p.m., 2 p.m., all the way to 8 p.m. And I have all my correct times, but they're matching with a certain x value that when plugged into the function gives me a certain t value, which is temperature.